So a resultant force, right, is just the result or the net, right? Another nice word is the net force. And this net force is the one that gives rise to the equation that you guys already know. Force is equal to mass times acceleration. Right, if we take the example that I've just given you, if we say that an object is in equilibrium, right? Equilibrium, that's a mouthful. What can you tell me about its net force, Keanu?
It's 0. When an object is in equilibrium, there's no resultant force.
Right, so the net force or the resultant force is 0. Right? So if you are sitting in your chair right now, you are stationary, you are not moving, right? Your net resultant force is 0, right? Gravity is pulling you down, but the contact force of the chair on your bum is pushing you up, and that's why you're not moving, okay? If you had to throw an object in a vacuum at a constant velocity, if no other force applies or affects the object, it will also remain at constant velocity, right? So the most important thing that we can take from this, if an object is in equilibrium or has a net result in 0, what else is 0, Dominic? If an object is in equilibrium, it has no resultant force, or sorry, its resultant force is 0. What can you tell me?
Its acceleration is 0.
Right, it has no acceleration. Okay. Right, and that's kind of an important thing, right? If you're working with a problem and very sneakily they give you a problem where the resultant force is 0 and they've asked you to work out acceleration, right? If you have a net resultant force of 0, there is no acceleration. Okay? And that makes sense, right? Because if we have no force, we have what times the mass will give you 0, while the only thing can be 0. So the acceleration must therefore also be 0. Right, time to draw pretty pictures. So I'm going to grab this pretty little picture down over here from your textbook. Right, when we are dealing with forces, and I'm sure the Keanu and Dominic can testify to this, you always draw a diagram to show what forces are being applied on an object, right? Because you might miss out some forces if you're not careful, right? So whenever we're asked to calculate forces in some direction or acceleration or whatever, right, the first thing we're always going to draw is some kind of a diagram, okay? So Twaya, do you see the aeroplane up on the screen?
Yep.
Now I expect that level of detail in your diagrams. You can see the windows, the wings are clear, the cockpit. I mean, they could have added the pilot in as well, but you know, that's the level of detail that I expect, right?
I could add the people's heads.
You could
I've
even
been doing physics wrong.
exactly. I'm telling you guys, if you're not drawing pictures like this, then you need some help. Okay.
Yeah, you know, if you squint, you can see the ailerons on the wings.
There we go. And
It's gonna be super detailed.
You could even add like a skydiver jumping out the back of the plane or something, because you know that really shows you know what's going on.
Well, that kind of looks like a passenger aircraft. So if someone is jumping out of there with a parachute, something's gone wrong somewhere.
Maybe it's the pilot jumping out. We don't know. Right? That means that at some point, I think the thrust is going to go to 0, which means the lift
Probably.
is going to decrease, which means it's going to go down, isn't it? Okay.
Oops.
So on a more serious note, obviously, we are not expected to draw fancy pictures like this. Okay? We are going to draw simple diagrams to represent the forces. So like in the textbook, I'm just going to quickly recreate this forces, right? Except I'm not going to draw an aeroplane. Usually, I think the convention is to draw some kind of a block, right, to represent the object that you are talking about. Okay. And now we're just going to, in the case of an aeroplane, we're going to express the forces that act upon it as arrows, right? And the arrows are always pointing away from the object, right? In the direction that the force is being applied, okay? So if we have to recreate thrust, right? The thrust is a forward force. Let's see if I can do this. Will it? Ooh, it'll let me swing it around. I like it. There we have the air resistance. Unfortunately, you guys will have to do this the manual way with your pens and pencils. So those are the forces that I can see acting on the airplane, right? So we can label them. This is the lift, right? This is the weight of the aircraft pulling down. We have thrust from the engines, and we have some air resistance, right? That air resistance is similar to when you're driving in a car. If you stick your hand out the window, the wind coming from the front, well, that's air resistance, okay? Right, Dominic, there's one more important piece of information that I have not included, and what is that?
A, it looks like at the
A?
top there.
So what is this A, right? I have just drawn it because I knew yesterday I was going to be very lazy. What is this A?
Isn't that in the direction that it's traveling?
Right, this is the direction that we are measuring the acceleration in. Okay? Now, the important thing about this direction of acceleration is, unless it's stipulated in the question, right, I can choose which direction I want to measure the acceleration in, right? Just remembering that acceleration is a vector. It has direction and magnitude, which means if I measure acceleration in one direction as positive, if I had to just change which direction I want to measure the acceleration in, right? If I'm measuring the same acceleration, this time it would just be a negative acceleration. Same value, just negative. And the negative is just indicating the direction. Okay? And this is very useful, right, when you're dealing with certain problems, right? Because it might be easier to deal with the problem if you can specify the direction that you want to measure the acceleration in. Okay? But when you're drawing your diagrams, you will tell yourself, right, I want to measure the direction of acceleration in this direction, right? So those are the important things that you need to remember, is we're going to always have the direction of acceleration, and we want to consider, right, well, for now, it's only going to be in one dimension, but in the future, we want to consider all the forces that are applying on the object in question. Okay? And later on, we're going to learn that sometimes they don't even look like this, right? They're at funny angles as well. We all good there? Nice, simple Twitter. You think you can manage a little block with some arrows sticking out of it?
Yeah.
Yeah. Cool. All right. So every question, all right, and even when you're doing your homework, every question with forces starts off with the diagram. Okay. Right, let's go and grab our questions for the day. Let me move my arrow because I know I'm going to need him just now. Right, here we have the example from our textbooks. Let's quickly run through this guy together. Let me make this a little bit bigger. Right, this is a two-part question. The first part of the question says a car of mass 600 kilograms has a driving force of 500 newtons and air resistance of 200 newtons. Okay? How long is it going to take, how long is it going to take to accelerate from 10 meters per second to 20 meters per second? Okay. Kiana, what are those numbers, meters per second and 22 meters per second? What quantity is that? Displacement, velocity, or acceleration?
The 22 meters per second is acceleration, but negative acceleration.
Okay.
Oh no, it is normal.
Yeah, okay. So that 10 meters per second is initial velocity.
And 22 is final velocity.
And the
I was
22
looking at B.
Okay. Oh, you were looking at B already, yes. Okay. So look at the units that you're given because it's a clear indication of what we're talking about. Okay. Just as a precursor as well, guys, when you're dealing with questions like that, it's not common, but sometimes the quantities you're given are not in the units that we use, okay? Remember, we measure when we're dealing with forces in meters per second. If you are given kilometers per hour, you need to convert those units to meters per second first, right? The same as if you're given kilograms, tons, for instance, or grams, right? The unit for a Newton is kilograms, so we need to convert the units first. So make sure you're using the correct units as well. Okay, we have to do two things here. We need to draw ourselves a diagram, right, of what's going on. And then we need to write down the information that we are given. Okay. So here comes my little block. Oops, sorry, that's not a block. This is a block, there we go. And it doesn't want to make a block for me. Right, Dominic. What are the two forces acting on the car?
Friction, which is 200 newtons, and then the pushing force, which is 500 newtons.
Okay, so the car has some kind of driving force of 500 newtons from the engines, and the air resistance is holding the car back. Come on. At 200 newtons. Okay. And we can specify the direction that we want to consider acceleration. Now, obviously, it would make sense to talk about the acceleration in this direction, because we don't actually want to get a negative acceleration. Right. Troya, what do you think is the first thing that we need to work out? If we consider that, right, we have, well, why don't we write the information that we've been given first, okay? So the information that we have is, well, we have the mass of the car.
600.
Yeah, we have 600.
Then the driving force is 500. Then wouldn't the, and then the air resistance 200. Then the stronger force is the driving force, but by 300 newtons.
Okay, so actually what we're looking for, if we consider what we have, right, we have mass, we have two forces, right, and we have some initial velocity here of 10 meters per second and final velocity of 22 meters per second, but they don't really help us right now, okay? So the equation that we most likely want to use is this one over here. Force is equal to mass times acceleration. Now, very importantly, when we're using Newton's second law, this equation, force equal to mass times acceleration, we need to remember that this is talking about the resultant force, the net force. Okay, so this is why we draw these diagrams, so we can see which forces are acting on an object. Okay, we need to resolve the forces and find the net force, the resultant force. And as you've quite clearly shown, right, these forces are acting in opposite directions. And because we are considering acceleration to the right in this example, the force acting in the same direction as acceleration is also going to be positive, right? Because remember, force is also a vector. It also has direction. Okay? And this force over here will be minus 200 newtons because it's acting in the opposite direction that we consider as positive. Right? We have chosen to consider the direction the car is traveling in as the positive direction. Right? So my net resultant force is going to be this combination of forces. We have 500 minus 200, right, equal to the mass of the car, which is 600, times the acceleration. Okay, and the acceleration is the variable we are trying to solve. Right? This is going to give me an acceleration of 0.5 meters per second squared. Right, now if I go back to what I've given, I now also have the acceleration. Let me move this guy out the way. And based on that, we now have enough information to find out how long it takes. Right? So we can just use the very simple equation, velocity is equal to u plus at, right? And we can just put the information that we have in, right? We have the final velocity of 22, we have the initial velocity of 10, we have the acceleration of 0.5, and we can solve for t, right? This will give me a time of 24 seconds. Any questions? Nice and simple. Okay, the key thing again, we draw the diagram first. We need to resolve the forces first. We need to find the net resultant force. And for the problems at the moment, we are only going to be looking at them in one dimension, all right? We will look at two-dimensional problems later on in the term. But for now, you'll only be resolving two forces. Okay? Well, not two forces, a force in, well, one dimension. So up and down or left and right. Okay.
Okay, that's pretty easy.
Well, for
You don't
now.
have to worry about the trigonometry part.
For
Control
now,
the
yes. So I think if you have a look quickly in the textbook, they do give you a warning that it's coming, right? So you will consider problems with objects in equilibrium in chapter 3. And where does it tell you? I think somewhere we'll be looking at more than one dimension in chapter 6, I believe. Right? So when we get to chapter 6, we'll be looking at forces in two dimensions. And then we will start having to use trigonometry and so on. Okay, let's quickly do part B, all right? It's not very difficult at all. So it says the car stops providing a driving force, right? So the driving force is now gone and the brakes are applied. It decelerates from 22 meters per second to rest in 220 meters. Find the force of the brakes. So the problem has changed. So Kiana, can I use the same diagram?
Yes.
Can I?
If you change some of it.
I need to change it. Okay, that's the important thing is I don't have a braking force or a driving force anymore. It's gone, right? So my original diagram is now not going to work. So the best thing to do is make a new one because it's going to take you 10 seconds. Okay, so let's quickly just make a new. Here's my car. Sorry, that's not a very good car. There we go. Toya, what do you think of my car? Do you think it's going to drive very fast?
No, not really.
Not really, hey. Okay, let's consider the forces being applied to this car. All right, we still have the air resistance that hasn't gone anywhere, so we still have. Come on, Mr. Arrow. We still have our 200 newtons. Right? We don't have the driving force anymore, so it's not there, right? Again, we are considering acceleration going in this direction, right? That's why my force of air resistance is minus 200 newtons, right? Just because it's going in the opposite direction. And the force we are trying to find is the braking force. So, Dominic, in which direction is the braking force going to be?
The same direction as the resistance.
Okay, the same direction, right? It's actually going against the direction of travel, right? And we don't know this force. This is the force we are trying to resolve. We're trying to work something out and we don't know it. We like to give it a variable. Let's call it F for force, the force. Right, and again, we're just going to take the information that we know. So let's write some pieces of information we know. We know the initial velocity is 22 meters per second. We want the vehicle to come to rest, so its final velocity is going to be 0. And we know the displacement that this took place in. Right, this happened over 220 meters. Now, when I see 3 bits of information, that makes me smile because that tells me I don't have a simultaneous equation. I just need to remember which equation to use, right? I'm trying to find the time. Oh, sorry, not the time. I'm trying to find the deceleration. Okay, so I'm trying to find A, right? If I want to work out force, I need to use the equation force equals mass times acceleration. I have the mass of the car. I don't know its deceleration yet. So I need to work that out. So running through your brain, you need to rummage through the drawers and think, okay, which equation is going to give me acceleration based on the information that I have? And it's, in this case, going to be v squared equals u squared plus 2as. So I encourage you to memorize these formulas so that you don't have to look them up. That wastes time, right? Just know them. You're going to use them a lot in any case. Right, and now we're just going to solve the equation. So we have 0 for the final velocity, 22 for the initial velocity squared, plus 2 times the acceleration, and the displacement is 220 meters. Okay? Again, very important, make sure that the units or whatever you're working with are compatible. Okay? If that was kilometers, you need to convert. Right, if we square that and divide by 440, we get a deceleration, right, of minus 1.1 meters per second squared. And that kind of makes sense, right? We should get a negative number because if you think about deceleration, it's acceleration in the opposite direction of the direction of travel. Okay? Right, now we've got enough information to solve for this force, right? We need to remember that this force that we're trying to solve, right, is in the opposite direction of the acceleration. Okay? We have minus 200 newtons, right? Again, it's minus 200 because it's in the direction away from the movement of the car, right? If I chose to choose my acceleration in the opposite direction, right, then the force would be positive. Okay? But because I've specified that positive is the direction that the car is traveling in, any forces that act in the opposite direction are negative. Okay? And so we will also have minus f, whatever f is going to be. Right, the car was 600 kilograms and the acceleration was minus 1.1 meters per second squared. And by the powers of your calculator, you can crunch the numbers and you will get the force equal to 460 newtons. And that is it. That is as simple as they get for now, right? So your step-by-step procedure really at this point will always be draw a diagram. List all the forces that are being applied that you're given, right? Don't skip any of them out because you don't think they're right. Write them on the diagram, right? Oops, sorry, that was atrocious. Right, specify the direction of acceleration. If it's not given to you, specify it, right? You need to choose a direction for which direction you want to choose acceleration as being positive. Use common sense if it's not given to you, right? And list the other information that's given to you, right? It might sound stupid and time consuming, but always write the information down that you're given. It really does go a long way because then you can see what you have, what you need, right? And then it's also easier to work out which formulas you need to use, right? And lastly, just remember that if you are only given small amounts of information, right? If you are not given enough information initially to solve something, it's most likely a scenario where you need to solve a simultaneous equation.